Welcome to our first session on some mathematics topics, and this time we're going to be looking into a calculus review. But first, a little introduction. These sessions are mostly organized for you to practice, to review materials that you may have not covered in full extent. This is joint work with faculty members here at the math department. In this case, myself, Julio Urenda, Marta Delgado, or Mark's coordinator, and or an administrative technician staff, Maria Barraza. So let's begin. What are the things that we have here in terms of the concepts that we want to discuss? Well, there are three things. There are the basic ones that are associated with the notion of an integral. The first one, which is that of an antiderivative. The notion of area, and the one that is associated with the definite integral. The intention is that we're going to tie all these three concepts together under a single theorem, which will be appearing at the end of the session. So the first one, that is probably the one that we are most accustomed to mechanically, is that of antiderivative. But why? Well, because it comes from the same notion of derivative. The question is the following. Suppose that you have a function. Something like this, right? Quadratic function. And we'll take a derivative of it. Then f prime of x is 2x. Nothing new under the sun in this case, power rule. But the question is, well, if I was to start with this function here, let's say only 2x, and I give it a different name. Call g of x 2x. The question now appears as the following. What functions appear as derivatives of this? Are such that f prime of x is equal to g of x. You may say, well, we already found ourselves one of them, which is this one, the quadratic function here, x squared. But are there any others? Well, in fact, there are. We immediately know the following. We see that, for example, x squared prime is 2x. Also, x squared plus 1 prime is 2x. We also have that x squared plus 3 prime is 2x. We also have that x squared plus pi prime is 2x. What seems to be the case is that the only difference among the functions that we have here is that they differ by a constant. So, something to notice. We see that among the examples, they all differ by a constant with respect to each other. So I wonder if this is really the case for all of them. And so what I'm going to do is take something that is slightly different. Not only a quadratic one, but what about something that is trigonometric? Take a look. Something of this kind. Say that I have the following function. Tangent squared on one side as my first one, and secant square of x as the other one. Of course, I'm going to take the derivatives of each of these functions, following a composition rule, the chain rule. So this would be 2 tangent of x times secant square of x. Now, that's for the first. For the second function that I have here, it would be f2 prime of x is equal, same thing, chain rule. You have 2 secant of x times the derivative of secant, which we know is secant of x times tangent of x. Now, after a moment, well, after just massaging this expression that we have here, look, we have similar factors, so we combine them. So we have 2 secant square of x times tangent of x. But then we see something that is very peculiar here. Even though the functions that we have here originally are very, very different. Well, at least in the form that they have. Their derivatives are exactly the same. So let me just point it out so that it becomes very clear. Notice that both the derivative of f1, the tangent square, and the derivative of f2 of x, the secant square, are equal. But do they differ by a constant? Right? Are the original functions differing by a constant? Well, here, who knows? Let's explore that. Let's see. Let me put them together. And, in terms of trigonometric identities, there's only one that I remember, and I kind of essentially forgot all of them, except this one, which is very fundamental, which is that of the circular associated with the unit circle. If you take the unit circle, x and y, you draw it, right? Then you measure an angle. Then the coordinate associated with on the unit circle with this angle would be given by cosine of alpha, sine of alpha, right? For this directed angle that we have here. Well, what is the meaning of that? Well, we can translate this into a trigonometric identity, which is that the cosine of alpha squared plus the sine of alpha squared is equal to 1. Then from this one, we can deduce some of the trigonometric identities associated with tangent and secant, which would be, well, what I'm going to do here is make an assumption and say that cosine square of alpha is different from 0, so I can perform a division. And in this case, what I'm going to do is make the following. And of course, this is the same as to say that the cosine of alpha is different from 0. That means that we're avoiding a particular some particular values of alpha. So the next thing to do is perform a division. So I have 1 over cosine square of alpha, and I'm going to multiply both sides of this equality to obtain cosine square alpha plus sine square alpha equal to 1 over cosine squared alpha times 1. Some simplification of this indicates the following. Well, multiply this term. I have 1 plus, well, I have sine squared alpha over cosine squared alpha is equal to 1 over cosine squared alpha. But of course, let me do some algebraic work here and obtain the following. From this, I have 1 plus sine alpha over cosine alpha squared is equal to 1 over cosine of alpha squared. But then this one, well, look, this is exactly the definition of tangent, and this is exactly the definition of secant. So we now translate this into the following. 1 plus tangent squared of alpha is equal to secant squared of alpha. So our surprise is not really a surprise, because when you take derivatives, we see that secant squared of alpha differs by 1 with tangent squared of alpha. So this says that, or it provides some evidence that there should be something underlying. There should be something here that is governing this notion of antiderivatives. But let's be very precise now, because now we're going to build it. It's no longer just some examples floating around. We have to have some precise definitions so that we can always refer to them when we need them. So we start like this. Definition. Let f of x be a function defined on an interval AB. We say that a function capital F of x on the same interval is an antiderivative. When I say n, because now we see that this thing is not unique. There may be more than one of little f of x, provided that the following occurs. When I take the derivative of capital F, it produces the little f. So with this in mind, right, we have now the following. We see that x squared is an antiderivative of 2x. But with this definition, we can also say that x squared plus 3 is another antiderivative of 2x. In a similar fashion as the things that we just developed, from the one that I just erased, I can say this. Tangent square of x is an antiderivative of 2 tangent of x times secant square of x. The same thing I can say about secant square of x being an antiderivative of 2 tangent of x times secant square of x. Okay. Now we have the definition, but what we need to do is to make a connection. We see, at least from the examples that we have, that antiderivatives differ by a constant with respect to an originating function. But Would this be the case for anything? Let's see. Let's take a look. For that, we have to be in a little bit more generality. So I'm going to take the following. I'll suppose that under these conditions, that two functions, suppose that f of x and g of x are antiderivatives of a function f of x. The question is the following. What is the difference of these two? What kind of function is it? The expectation from the examples that we have is that this must be a constant. Okay, let's start with the easy part. Let's say that you already have, you're already being provided with a couple of functions that differ by a constant. Suppose that f of x and g of x differ by a constant. So what can we say from here? Well, let's call that constant c. So I'm going to say f of x minus g of x is equal to c. Now, what I'm going to do is take a derivative for c. Well, then f prime of x minus g prime of x is equal to c prime. Well, but let's not forget what we have here is a constant. Well, the derivative of a constant is 0. So we have that f prime of x minus g prime of x is equal to 0. So indeed, if I compare these two, what I have is that f prime of x is equal to g of x. In other words, whenever the conditions are there available, and I have two functions that differ by a constant, well, they are the antiderivative of the same thing. Now, but that was the easy part. Let's go in reverse. If I suppose that two functions are antiderivatives of one, would they differ by a constant? Let's see. So under the conditions that we have there, suppose that f of x and g of x are such that f prime of x and g prime of x are equal to f of x. Now I have to impose some conditions here. And those are the ones that are associated with the actual definition. So what are the conditions that we have here on f? First, well, f of x is differentiable, let's say continuous on a closed interval a, b, and differentiable. Well, actually, what we have here is that these two are differential, right? I really don't have to put this condition. But let's digress. So from here, what I'm going to do is construct another function that is going to be made of these two. I'm going to set h of x to be the difference of these two. What I'm really trying to find is whether this actual h, well, is a constant. But let's see. Let's see. What is h of x? Well, what I'm going to do is make the following. Suppose that h of x is defined on an interval. An interval I. And then from that one, well, what I'm going to do is make a restriction and further suppose and take two numbers, A and B, in this interval here. Okay, now what do we know? Of course, I'm taking some freedoms here in terms of making this as illustrative as possible. But what can we say about h itself? Well, we know that h of x is differentiable. How do we know that? Well, because the derivatives of both f and g are there available. And well, we have that h prime of x is nothing else but f of x prime minus g prime of x. So now, the thing that we have to or initialize with is to think about the following. Well, what properties do I know about functions differentiable on intervals? Well, let's bring the prior knowledge. What do we know about differentiable functions on intervals? Well, there are a couple of theorems there available. For example, we have Rolle's theorem, we have the maximum theorem or the minimum theorem, extremum theorem, but we also have the mean value theorem. What is the mean value theorem? What I'm going to do is to provide a picture. When you have a function differentiable in an interval, and you say that it is differentiable on that interval, then, well, we look at the values that it has. That would be the x-axis, this would be the y-axis here, and I have y is equal to f of x. So the values that I have in this picture, here I have f of a, here I have f of b. Then I look at the average, the mean of these two values on this interval, meaning the following quotient, f of b minus f of a over b minus a. I'm just bringing a picture so that we can have some geometric intuition of what's going on here. So what happens is that if I draw the secant line joining these two, the slope of the secant line that I have here is exactly this quotient. So, but if just looking at the picture here, you can see that there should be another point somewhere here for which the tangent line is parallel to the secant. I'm going to use a different color. Hopefully, it will be showing up in the picture and in the video feed as well. So I'm going to give that a different name. I'm going to call this C. So what this is saying is that we should be able to find another number C in that interval, for which the derivative at that C is equal to this quotient. And that is the statement of the mean value theorem. But then, can we use this information here? Well, let's take a look. What do we know? We have our function h of x equal to f of x minus g of x. Let's not forget, f and g are both antiderivatives of the same function, little f of x. So I'm going to state that here. We know that. What if I apply the mean value theorem on my function h? Well, taken from the picture here, let's not forget this f is different from the one that I'm thinking of originally, because this is just for the picture itself. But what is that's going to happen? Well, let's see. The mean value theorem states that the following should take place. If I have h evaluated at b minus h evaluated at a over b minus a for whichever two values that are on the interval, of course, with certain restrictions. That is supposed to be equal to what? Well, to some h prime of c, where c is located between a and b. But then you say, well, wait. I know what this is. I know that h prime of c, well, is the difference of f prime evaluated at c minus g prime evaluated at c. Then you say, well, wait a second. What I have here is that this two, well, are antiderivatives of the same function. Well, from that, we can say that f of c, which is the derivative of this one, right, minus f of c, which is the derivative of that one, well, equal to this difference, but this difference is 0. And what happens with a function whose derivative is 0? It must be constant. Okay, so we arrived to the result that we were looking for, is that any two antiderivatives, of course, on the same interval, because we can easily see that this fails if we're not talking about the same interval. And I'm going to mention that because it's really important that we know the restrictions. Suppose that you have a function that looks just like this. But now I'm going to define it on 1, 2, and then on 3 up to 4. This would be the domain of definition. And then just from a picture, I'll draw it here, level at 1. And then I draw another line here, level at 2. Well, when I take the derivative of this function over here, it's 0. When I take the derivative of this function over here, it's 0, but clearly the difference is not 0. The problem is that it's not that the theorem that we are stating here is false. The problem here is that we're not working with the right conditions. We're not working on a function defined on an interval. We're working here on a function that is defined, well, in a disconnected domain. So, what will be the next thing? You may say, well, look, based on these observations, we can say that once we find an antiderivative, we find them all, because they just differ by a constant. So, now we are in place to make the following. Let's find antiderivatives of functions that we know. And let's find them all, once and for all. Well, let's say the following. So we're a linear one, x. What should be the antiderivative of x? Well, we have to see. I need to find a function that when I make it into a derivative of it, it returns me x. Well, once I find one, then I'll find all of them. Well, let me find one. Here's just by guessing, essentially. I'll take x squared divided by 2. Why that? Well, because by the power rule, when I take the derivative of x squared, it becomes 2x, but I have to get rid of it. I'll just make this. Okay, that was easy. But to find them all, I'll just introduce another symbol and say, well, C, for some constancy. What about something that looks like this? You may say, well, if it comes from a power, it has to be a power that is just one more. So that when I take the derivative, it becomes one less. So the power must be 3. So x3. But when I take this one and just take the derivative, I introduce a factor of 3. Well, let's get rid of it by division. But then look at the pattern that we have here, just developed. If I use it for 4, I think we can do the same thing for all the others. You see, I just have to increase the power and divide by that increased power. I have x to the 5 over 5 plus c. In fact, I can do this for whichever power except -1. Why is that I cannot do it for -1? Because I will be introducing a division by 0, which is clearly not something that we're allowed to do. So we now have the following power rule for antiderivatives. Suppose that n is different from -1. Then the antiderivatives can say d because I'm going to collect them all, x to the power of n have the form x to the n plus 1 over n plus 1 plus c for some constant c. Essentially, what we can do here is just revert the rules that we have been introduced to. Which ones are those rules? Well, here we have an antiderivative version of the power rule. What about the trigonometric ones? Well, we know, for example, that if we take sine of x and compute its derivative, that should be cosine of x. So what we're going to do is just invert this relation and say, well, from this that it is known, we're going to produce the following rule. The anti of cosine of x, well, they all look like sine of x plus some constant. One more. If you take, let's say, cosine of x, and you take its derivative, well, that is negative sine of x. Well, we don't really like negative rules, so I'll take that one, introduce a negative sign here, and now we get exactly what we want. You say the antiderivatives of sine of x are of the form negative cosine of x plus c. And we can play this game for all the rules that we have in terms of differentiation. Now, you may not find it in this fashion because writing this is quite cumbersome. But for that, we introduce this symbol, which is probably the one that you have seen. The indefinite integral sign. So instead of writing this, we would write the indefinite integral, meaning the antiderivative of x to the n dx is equal to x to the power of n over n plus 1 plus c. We should not forget that we're working with functions. Inside of this, there are a few things that we should mention. We are talking about antiderivatives, and with each of these things, there's an association with a domain. And that domain, to make sense, and for the uniqueness part to take place in terms of difference up to constants, we should be working on an interval, right? On the same interval. Let's not forget that part, right? Now, if I want to simplify this rule, of course, this for n different from -1, in order for this to make sense, we say that the indefinite integral of cosine of x dx is equal to the sine of x plus some constant. Of course, this is defined on the entire real line, so this makes perfect sense. I would say that the indefinite integral of sine of x dx, just to make a marking, this is just a dummy symbol to indicate that we are using the variable x, but that's about it, right? It doesn't have any other meaning. It's just a placeholder. Would be the negative of the cosine of x up to a constant. It's a lot of words. It's a lot of meaning. But we have to be careful that with this introduction of symbols, right, it doesn't mean that we have area here. It doesn't mean that we have just working with some random function. No, we have to be precise. Although the symbol is very, very useful and very efficient to demonstrate the relation, it hides important information, which from time to time tends to be forgotten. That we're working with functions defined in a particular interval. So, the next part. And for that, I want to make the following connection. The area problem. So, we know how to compute areas of certain shapes. For example, squares, rectangles, polygons, some special curves like circles, and that's pretty much it. We don't know anything else. In fact, that's all that we know. And here I have this question. I'm going to draw a line segment. Something along these lines. Let's say I'm going to draw the line y equal to 2x plus 1. Just to have some reference. Here I have my x-axis, here I have my y-axis. And what I would like to do is just to get some idea of how this line looks like. Well, let's see, just gonna make some, I'm gonna plot it. So let's see, where is it this touches the x-axis? Well, it touches the x-axis. On the first coordinate satisfies the following equation, which is that of 2x plus 1 equal to 0. So I would say, well, this is equivalent as to say that 2x is equal to -1, which is the same as to say that x is equal to -1/2. So somewhere here, I have it. Now, where is it this touches the y-axis? Well, let's see. I just have to make a substitution. So I would say, well, essentially, I'm solving this equation. Y is equal to 2 times 0 plus 1. Oh, that was easy. So somewhere here. Just plot it. 1. Just like that. Then I ask the following question. Starting from here, I want to measure this area. Now, that shouldn't be a big complication. Why? Well, let's explore what we have here. I'm going to take t to be a positive number. So that is my t. Right? The question is the following. What is the area of the shaded region? Well, there's not much that we can do unless that region is something that we are familiar with. But then we say, oh, look, I think we know what that thing is. This is a trapezoid. Look, we have a quadrangular polygon where two of the sides are parallel. It's just that it's tilted, but we're usually accustomed to see trapezoids in this fashion. Something like this, something like that, just like that. In this case, it's truncated. It looks like this. It's kind of exaggerating here, right? But that's the shape. And it's not so much of a problem to actually compute the area of a trapezoid. All that we need to do is to make a complement. So I'm going to call this capital B and this lowercase b. What I'm going to do is make an extension. I'm going to impose a line segment B on this one. I'm just going to extend it. And I'm going to extend it all the way up to this point. I'm going to drop a line here, vertical, and then ask myself, well, what should be this length? If this is B, well, by geometric properties, it's better be that this B is the lowercase b, right? This length that we have here. Well, then we say, wait. Everything that we have here is just right angles. The full thing is a rectangle. So the area of the rectangle is what? Well, is just, let's see, base times height. Let me give it a name. I'm going to call this h. So now I have h times b plus capital B plus lowercase b. That's it. Oh, but then look, what I have here is that this trapezoid is just another copy of this one. It's just that it was just transformed by rotations and translations. So I think we're done. Symmetry, these types of modifications or transformations on the plane preserve the area. So what would be the area of the trapezoid? Well, just half of that of the rectangle. So the area that we have here is nothing else but h times b plus lowercase b over 2, which is where we find this derivation, or you may have seen this formula before. Now, how do we interpret these symbols that we have here over here for our problem? Well, you may say, look, this segment that we have here plays the role of h. The segment that we have here plays the role of b, the big one. The segment that we have here plays the role of lowercase b. So I ask myself, well, if that is the case, all that I need to do is to find lowercase b and uppercase b. But that's not as complicated. That's actually very easy. This one might be interpreted as a function, right? So I want to know the coordinates of this point. Well, the coordinates of that point are t, comma. Well, the second coordinate being on the line is going to be provided by this instruction. So 2t plus 1. Okay. Now, one more thing. What if I look at this one? Well, this one is not actually that difficult. Actually, we did it already, but we can say that this is, well, 0. This is the origin, comma. Well, that should be 2 times 0 plus 1. So this point has coordinates first as 0 and second as 1. Okay. So that indicates that this b is actually 2t plus 1. While this lowercase b is just plain 1. Okay. So based on this observation, what should be the area? What should be the area of the shaded region? Let me erase it here. Seems no longer necessary. the area of the shaded region is, we're going to express it, well, H, but H is T, times, well, the sum of these two. 1 plus 2t plus 1. Okay? Divided by 2. Let me simplify that expression. I don't really like it that way. So now this is t times 1 plus 2t plus 1 divided by 2. Well, let's see. This should be, I'm going to do whatever is inside the parentheses first. So this is 2t plus 2 divided by 2, which is, well, t squared 2 plus 2t divided by 2, which is just t squared plus t. Okay. But then, wait. Look at this thing. Just as an expression. And let's examine the second coordinate of this point, which is actually indicating us how to locate points on this line. 2t plus 1. I'm going to put them together. So I have t squared plus t on one side, and then t plus 1. Then I look, are these two expressions here somehow related? So, well, let's see. Well, it seems to me that they're related by differentiation. If I take the derivative of this expression, I obtain this. But wait, weren't we measuring area? The original problem was measuring area. And now it seems like there's a relation between finding the area and finding an antiderivative. The area defined by this function, under some constraints here. But I can certainly say this. This thing that I have here, well, is an antiderivative of that. But this one, I have to say it, represents the area bounded by, well, the lines x equal to 1, namely this, x equal to t, of course, positive t, otherwise it makes no sense. This is the way that we have it. And the line y equal to 2x plus 1. But you see, what we have here is just a recasting of this. I mean, it's too much to be a coincidence. Too much. Let's try something a little bit more complicated and see if we can deduce something similar. Of course, we have to expand the things that we can do, because there's only so much that it's possible with these shapes. Let's see. The area problem or a parabola. This is what I'm going to do. We have to increase the complexity of things, but only step by step. Only so that we can refer to things that we already know. So, the same type of reasoning can be performed for any linear function. So what I'm going to do is increase the complexity to a quadratic one. And the simplest quadratic function that I can think of is that of x squared. And then I ask myself, if I make t positive, what is the area of the shaded region? Well, unfortunately, the region that I'm looking for, well, cannot be computed directly. Why? Well, it's not a polygon. The only ones that we know how to compute directly are polygons, because we can make triangulations, play here and there. But here, this is clearly not a polygon. The curve that we have here disallows that more than anything. We see, and this way, we can be sure that we cannot do it with a polygon, because for this to be a polygon, it should have constant slope, at least up to certain intervals. No, this doesn't have constant slope. Look, if we look at the tangent line, at any point, it's actually increasing. Right? So we say, what can we do? Well, here's an idea. If you're going to compute it directly with polygons, let's approximate it with polygons. And hopefully, that will result into something that is meaningful. So the idea consists, at least in this case, of undershooting and offshooting. So I'm going to simplify the problem. No, I'm not going to simplify anything. I'll do it in the way that it should be. So I'm going to take this. I'm going to make a gross approximation. You know, I have this interval from 0 to t. And what I will do first is try to approximate this with rectangles. You say, well, how many do you want? Well, let's say 2 rectangles. And to make things a little easier, 2 rectangles, and then you have to make a decision. Well, if you want 2 rectangles, where do we place the divider? Well, let's say that you put it halfway, somewhere here. T divided by 2. Well, over that, well, we have a lot of choices, right? But let's just stick to this one. Let's say that I'm going to use that and that. Immediately, just from the geometry, we observe the following. Yes, this is an approximation. Let's calculate this approximation. We know a few things. Certainly, the area defined by the lines x equal to 0, that one, x equal to t, and y equal to x squared is, well, is less than the one provided by these 2 rectangles. But let's compute them directly. No, what is that area? Okay. The first one, well, let's compute the height. The base is easy. The base is t divided by 2, the same as this base, which is t divided by 2. Okay, t divided by 2. Oh, okay, that was fast. So the base is the same. What about the height? Well, the height, well, is associated with this point. And the height of this one is associated with this point. Let's find the coordinates of that point. Well, that should be t times t on the first coordinate, and then t squared on the second. What about the coordinates of this point? Well, this one is on the x-axis is t over 2. So I'm going to just take it over here so that we can see it. That is t over 2. And the second coordinate is the square of the first. So that should be t squared over 4. Okay, so the area that we're providing here is going to be given by this. Base times height, t over 2, the base of this, times the height, t squared over 4, plus base times height, t over 2, times, well, t squared, whatever that is. Maybe we can do some simplifications here. For example, I can say, well, this is, I can factor that out, and I have t squared divided by 4, and here I have plus t squared. Maybe you can factor a few more things. For example, I can factor t squared, and I have t over 2 times t squared times 1/4 plus 1. Okay. That's a little easier. In fact, this is what t cubed divided by 3 times 1/4 plus 1. Okay, but certainly what I have here, it's greater than the area that I'm looking for. Now, let's do this. Since there's no guarantee that the area that I have here, somehow, as I make more partitions, is going to progress to the one that I'm looking for, I'm going to try to squish it. So I'm going to offshoot, and I'm going to undershoot. And hopefully, as I progress in the number of divisions, those numbers will converge. Let's see if that happens. This is overshoot. It's undershoot. Same picture. Same subdivision. But now this time, instead of using these rectangles, I'm going to use these two. This one a little bit degenerate, not in the sense of being evil, it's in the sense that it's a rectangle with no area, right? But anyways, we're going to introduce it so that everything is a schematic and we remain doing the same things. So, some computations. The lengths of the intervals that we have here, t over 2, t over 2, remember, it's positive, so this makes perfect sense. What else? Well, the coordinates are actually the same. This one that we have here is just t over 2, comma, t squared over 4. Same thing. But what about this area that we're reflecting by these two rectangles? Well, in this case, the area the two rectangles, not between. And let's see. I'm going to do it anyways. So this is t over 2 times, well, times 0. That's the height of this. Plus, well, t over 2 times, well, the height of this one, t squared over 4. Okay. This is what I have now. This reduces to t cubed. Why is that to be here? It should be. Sorry. Should be it. But for this one, well, we have t cubed over 2. And I'm going to leave the quarter there. Only because the quarter is also here. And I really want to relate these quantities if they're going to reflect what I want, the notion of area. So, but you see, in this process, I made several choices. Because first, I decided on this side to take rectangles that are overshooting the area. Here I'm using quotation marks. And here, I'm using rectangles that are below, right? So they undermeasure the area. Let's do the same thing, but now with 3. With 3 instead of 2. And see if there is a pattern that may arise so that we can use it. Because at this point, well, there's really not much of information, except that we have this. Let me collect what we have and just annotate it somewhere here on the board. So for whichever notion of area that we have, we know this. T cubed over 2 is less than or equal than the area that we're looking for, which is less than or equal than t cubed over 2 times 1/4. And again, quotations. Now let's use 3 rectangles. And to make things, let's say, easy enough for us to handle, equally spaced with exactly the same base. Otherwise, we're going to just be going crazy. So, another approximation. And again, this is in quotation because I'm not really sure if that's actually going to happen, right? This is just some intuition. Hopefully it happens. Who knows? Okay. Same thing here. T positive. But now I'm going to divide this in 3. So I know that this length is t over 3. This length that I have here is t over 3. And this one is t over 3. Equally spaced. Okay, now I want to draw these line segments that touch the curve y equal to x squared. And, well, I'll proceed in exactly the same way that I did it before. Overshoot. Undershoot. Now, let's look at some things that are common here so that we can actually compute something efficiently. Otherwise, it's going to be a nightmare. Let's see. All of the rectangles here have the same base. So we may factor that out. Now, let's examine the coordinates of the points, because those are really relevant. For this one, we have, well, what? T over 3 times the square of that, which is t squared over 9. This one is actually, well, let's look at this. It should be 2t divided by 3. So the point that we have here is nothing else, but, well, the second coordinate of this point would be 4t squared over 9. Okay. And, well, for this one, we have simply t squared. But now, look, instead of writing it just in that fashion, I'm going to write it with the same denominator, just to see if I can collect more things. So this one, I will express it as 9t squared over 9. Now, this point is also of interest for us. 0, 0. But, well, we may express it, of course, as 0t squared over 9. Because we're going to use it. Right? Okay. So, what about the base using the distributive rule or multiplication? What will be the height associated with this? Well, it should be t squared over 9. The height associated with this, it would be, well, 4t squared over 9. The height associated with this, well, plus 9t squared divided by 9. Now this is paying back, because from here I can factor a few things, and I have t. Actually, I can factor t squared from everywhere. Huh? So I have t squared, t times over 3 times 9, and what I have here is, well, 1 plus 4 plus 9. Oh, that's not so bad. Actually, this turns into t cubed divided by 27 times 1 plus 4 plus 9. This is the overshoot. What about the undershoot? Well, similar idea, same base, t over 3 times, well, remember, the height of this rectangle that I have here is actually 0, but I'm going to express 0 in this fashion so that I can use it 0 over 9 times t squared. And then essentially it's going to repeat, but only up to these two terms. So I have plus 1 times t squared over 9 plus 4t squared over 9. Well, for this one, I have t over 3 times, I'm going to factor that one, I'm going to factor the 9, and I have 0 plus 1 plus 4. And I think a pattern is starting to emerge. We followed exactly the same scheme, exactly the same one. What we're going to observe is that instead of now using 3 rectangles, we're going to use 4. Well, we're going to get this. You overshoot. Well, we equally divide the lengths by 4. Then we compute the lengths associated with each of those subdivisions. The first one would be, well, t squared divided by 16. The next one is going to be, well, twice t squared divided by 16. The next one is going to be, well, I should have 4, so that should be 3t squared divided by 16. Actually, I'm hiding a few things here, but well, we're going to see it. Plus, the next one would be 4t squared divided by 16. Now we use 4 rectangles. The undershoot, well, divided by 4. Now, see, this time we're going to start at 0. So I have, I'm going to actually write it in this fashion. 0 over 4 times t squared. The next one, 1 times t over 4 squared. The next one, 2 times t over 4 squared. The next one, 3 times t divided by 4 squared. Let's see what we can factor from this to overshoot and undershoot. From here, I can factor t squared from everywhere, and I can factor 16. And what is it I'm left out with? Well, I have t times t squared over 4 times 16. And for this, I have 1 plus 2 squared plus 2 squared is 4 squared. And I'm going to leave it in that way. For this one, I have t. I can factor t squared from everywhere. I can factor 4, and I can factor 16. But then from here, I will have 0 squared plus 1 squared plus 2 squared plus 3 squared. And that's a pattern that we can explore actually by induction. We can verify it. This is not a course on introduction to advanced mathematics, but let me show you. I know there's a lot of computations here. There's a lot of things that we're doing. But what would happen with 5? Just extrapolating a little bit. Five rectangles. Well, let's see what is that we have to modify. Well, we will have to modify under the overshoot. T over 5. For that one, it's going to be t over 5 squared plus t 2t5 squared. I'm just advancing here. Plus 3t over 5 squared plus 4t over 5 squared plus 5t over 5 squared. Bam. For the undershoot, I will have t over 5, but now I'm just going to start just like this. And I will have t0 time over 5 squared plus 1 times t over 5 squared plus 2t over 5 squared plus, well, let's see, what is that we have here? 3t over 5 squared. I need the 5 terms. So I'm having 5 rectangles. So now it's 5. We're done. Now, let's extract information from here. So, look, this time I'm not going to develop the denominator. It seems very useful to have it in its full form. From this one, I can say, well, look, from here, from all of these ones, I can factor t squared. And from the denominators, I can factor 5 squared. Well, I'm going to introduce it. T over 5 times t squared over 5 squared times, well, 1 squared plus 2 squared plus 3 squared plus 4 squared, 5 squared. This one, basically the same. T over 5 times. Now, starting at 0. Now, what if instead of having 5, I have n of them? The formula that we have are going to turn into this. Overshoot. Well, let's look at the patterns that we have just developed here. That should be t over n. Of course, n has to be greater than 1 or equal, right? For this to make sense. Times t squared over n squared times. Look, what we have here is the sum of the first n squares. That would be 1 squared plus 2 squared plus 3 squared plus n squared. The positive n squares. What about the undershoot? That would be t over n times t squared over n squared times 0 squared plus 1 squared plus 2 squared plus n minus 1 squared. Now, the question is, what happens when we take limits? What happens to these expressions as we take limits? Now, time is not going to allow me to continue with the full computations, but this one, as I let n tend to infinity, will become q over 3. And this one, the same. Exactly the same. And you can verify this manually if you like to. Just have to refer to the formulas for this, for the sum of the squares of positive integers. Now, what is the meaning of this? If we examine these expressions that we get, look, they're identical. That means we're overshooting, we're undershooting. And as we progress, we'll all go to the same place. This one. And if we go to the same place, well, that's a good definition for area. And then in this fashion is that we define the area in these terms. The connection between, unfortunately, time is not enough, but now we can see also that even in this example, if we take the derivative of this with respect to t, we'll return to the original description of the parabola. And well, with this, I would like to conclude. I really would like to go into further details, but well, time will not allow us to do it. So I really hope that you enjoyed this session. I look forward to see you next time, because this is something that I have in mind, that I think it's super important to define it in these terms. What in the world is this? Do we know what that is? I don't think so. But next time we'll define it using integrals. Oh, see you next time.